Okay, welcome. This is the last class. Sorry for my flu. We'll try to get through it. I want to finish a few items from the dynamics of deep networks of last class, and then make a few considerations back to the old class and to the foundations of the machine learning approach that we have been looking at. So first of all, let's finish a couple of things depending on time. I would like to just summarize that we were interested in the dynamics, how GD, gradient descent, gradient flow converges, and to what. And the reason is really to understand if there is any complexity control that take place during this convergence. This has been a topic in the last 3 or 4 years, whether there is kind of implicit regularization or maybe something due to flat minima or so that provides good performing solution to gradient descent. We have gone through a couple of properties of networks, in particular the homogeneity property of, this is true not for every deep neural network, but for RLU networks. And this allows us to write a neural network F, which usually is a function of weight matrices at k, at 1, and of course input x as rho f tilde, where this is now in terms of normalized weight matrices, and rho is the product of the Frobenius norm, say, or another norm, but say the Frobenius norm of the matrix of each layer. So and then one can look at gradient descent, which will be gradient descent with respect to the weights V of the loss function L, and this will be in the special case of the exponential, the sum over n, the example of yn, which is a binary variable, rho f x. Now, we have seen instead of this unconstrained optimization that I can do, of course, on VK and also on rho, giving me 2 sets of gradient descent equations. I can consider also the constrained optimization, which we did last time, in which we do the same optimization, but we impose during the optimization the V to be norm 1. Okay, so this was here, where you introduce a set of Lagrange multiplier one per layer. And then we went through the situation in which we have a fixed row, and we're looking at the equations gradient descent in V, and one point we had a little discussion, I want to clarify this, is we can find the value of lambda k from the constraint at Vk, the norm of Vk equal 1. And the way we do this is especially for Sasha, this is, we know that if Vk norm is 1, then the derivative of temporal derivative of Vk square is, which is 2 Vk transport Vk dot, must be equal 0, because Vk, the norm 2 is constant, is 1. So that must be equal 0. So this means that under this constraint, transpose of Vk times Vk, these are vectors, dot, must be equal 0. And so by using this, so I'm using this property, and I use it by deriving a new equation from this one by multiplying on the left by Vk transpose. So I have Vk transpose V dot under the constraint that must be equal 0. So I set 0. And then I multiply on the left the right-hand side of this equation. And what happens here is that I have Vk transpose times df dvk. And because of the structural lemma, this is equal to f. Do you remember the structural lemma which we had, that considered as vectors Vk transpose df dvk is equal f. So this is exactly what happens with this term here when multiplied by Vk. This term here, by multiplied by Vk transpose, this becomes 1. And so what I have at the end is this equation equals 0. And I can now solve it for lambda. And lambda, 2 lambda comes out to this. So now I have a value of lambda, and this would be also a value that changes with time, with rho, in fact, that ensures me Vk norm equal 1. I can plug this in the original equation here and obtain this final equation without the lambda. Is that clear? Sasha? There are different ways to obtain this, so this is one of 4 different ways. You can check that in this way the norm of Vk is 1. From the point of view of the algorithm, in terms of running gradient descent and keeping the norm of Vk constant, one way is a Lagrange multiplier. Another way is, which is the coarsest one, is to renormalize at each iteration, essentially to reset vk equal 1 at each iteration. There is another one with the tangent gradient technique, in which you are projecting the gradient on the sphere of vk norm equal 1. And they all give the same result. Yeah. Sorry?
Where do we use the fact that the norm of vk is, so would the proof still go through if we impose the norm of vk to be some other constant?
Yes, it will go through. The constant, look, we, this first property, that this is 0, does not depend on which constant. When we multiply by, on the left, by V transpose, the 0 on the left does not depend on which constant. This term here, which gives 1, that will change if you have a different constant. So the constant will be taken care of. Okay. So we have seen so this should be the dynamic equation under this Lagrange multiplier constraint, and of course the stationary point of the gradient, where the gradient should stop for V, are when this is 0, and of course this term will go to 0 at infinity, because rho will grow more slowly and slowly, but to infinity. But this can go to 0 earlier if these terms will be 0 at some point. And because it's a mixture of terms, what happens that they can be 0 when they are reduced to 1 or a set of equivalent 1. If you look at here, among all the xn, the sum over n, there will be 1 or more with the same value of fxn, which will be the smallest of all. That's called the margin. Those will be the ones that are farther from zeroing the exponential, because I have the smaller positive exponential. They will be the ones that survive when the other ones are already 0 or negligible. When you have, say, assuming one of them left, then this will be a function of one variable, say x star, same here, and that equation can be satisfied and in this case you have convergence to maximum margin. One question is whether convergence is stable or not, where before time goes to infinity, for any finite time, the Jacobian of f, the Hessian of the loss, is negative definite or not, and I can show you later that it is. Before doing this, we have also seen that if we don't have the constraint of the Lagrange multiplier, but you look what happens to the normalized part of W, then you get the same stationary points, which is a little bit surprising. So even in the unconstrained gradient descent, you get equations that are slightly different. There is a different rho factor here, but the zero of this set of differential equation, one for each of the weight, is the same in both cases. You have this term in parentheses, which is the same. So one point also that we saw last time was that maximum margin solution can be regarded as minimum norm solution in the following sense. And I did it as essentially for a one-layer network. Here I'm doing it for the multi-layer network case. We have a multi-layer network which is f of the various weight matrices. I have homogeneity, so RLU. So if I multiply a matrix at layer k by some positive number alpha k, this is like multiplying this f by alpha k. Binary classification, I'm assuming we are in the separability regime, so that f of xn, yn is greater than 0. And so the maximum margin problem is to find the maximum over all the wk of the minimum of the margin of f, margin being the minimum over the training example of yn f of xn. This subject to the norm of each of the layers equal 1. Okay? That's the maximum margin. And this is similar to the definition in the case of support vector machines, only that here we have several W instead of just one. Now, we want to show that this problem, the maximizing the margin, is equivalent to this other problem, which is minimizing the norm of the W subject to subject to the margin being at least 1. So I want to claim is that problem there is equivalent to minimizing the norm of wk for all k subject to this constraint. And the proof goes through a few steps in which you have that this margin can be written in a slightly different way as the maximum over gamma of this expression being greater than gamma. So I want all of them, including the minimum one, to be larger than gamma. Is that okay? Then the max margin problem, this one using this definition of margin can be written, new definition of margin can be written in terms of gamma as the max over gamma maximizing over WK, W1 gamma, and subject to WK equal 1 for all K with YF larger than gamma for all I. So, so this have to be larger than gamma, and this implies that since it has to be true for this equal 1, I can normalize here. Because of homogeneity, I'll take it out. So this whole thing, including this condition, is equivalent to this divided by the rho, the norm of WK, W1, and so on. That has to be larger than gamma. Sorry? Yeah, it's one of the condition. Sorry?
Your rho is Your rho is 1.
No, rho is not 1.
Isn't rho the norm of the W?
Yes. Why should it be 1? Well, this says that YFWK and greater than gamma, subject to WK equal 1, right? So
Assuming that your function in neural network has norm 1 layers, but then the rows are 1.
I'm interpreting this saying that I have this margin larger than gamma, and this, if I impose WK equal 1, then has to be true, right? So I want to impose that WK has norm 1. And in order to do this, I divide here. I divide here, say, by WK like this. And but this is the same as not dividing here and dividing outside because of homogeneity. Sorry?
The first line is for arbitrary W's, not for uniform W's.
They are two separate, yes. How should I write?
So the first line is for arbitrary W's.
Yeah, it's for arbitrary W. I want to impose this, so I'm saying, okay, I think you are right. So let me see. I have for arbitrary W, but then I want this plus is that better? Union. I want to impose that. I want to have that condition plus the fact that it has to be hold for WK equal 1 is equivalent to what comes next. If you want two conditions. Let's go back. We are correcting things, which is, I think, is appropriate, interesting for you guys. I lose gamma then, right? Probably does not matter. Do you see what I'm saying? I can certainly avoid that, divide, but then I have to divide the gamma by rho. I think that's probably a better way to do it. You're right. So in which case, this will be larger than gamma prime, and this would be let me say gamma second, and yeah. Yeah, nothing should change here. We'll check, but I think you can conclude in the same way that going this route, you make it, you show that it's equivalent to maximize the inverse of rho, which is minimize the product of the norms of the W's.
Product of the norms of W's is different
From rho. Yeah. Yeah, you're right. Um, why do you think the product of the norm is different from the norm of the product?
So which specific norm are we using here?
Sorry?
Which norm are we using here?
Frobenius norm.
Oh,
Sorry? No, I was just making. He was asking with norm. I said Frobenius just for.
yeah, but the, like the product of norms is not the product of matrix for all norms, but for Frobenius it is. Right?
Well, actually, you can bound it, but it's not equal, right? So.
I'm confused on this holds in the linear case, this holds only for the L2.
For the.
In the linear case, this only holds for the L2 norm. The margin is equivalent to only the L2 norm. So you cannot be getting general norms. Anyway, we can take it offline.
Yeah, let's discuss later. That's it. I think we have this also in the deep learning case, but not from this argument. So. Now, the other thing we have looked, and I mentioned already, is that, and this is here the level of intuition, is that during gradient descent, after separability is reached, after essentially all training points are classified correctly, so that f of xn time yn is positive, then the various terms of the exponential in the loss function decay. The ones that decay fastest are the ones that are farther from the margins, so farther away, larger value of f of x. The one who survive will be the margin, the ones with the smallest values of f tilde. You know, the worst essentially of the training points. And if one is left while rho is growing, at some point one is left, then instead of having a sum of many terms, you have one term, and this will can be zero and will determine convergence to a minimum, a stationary point, which turns out to be a minimum, and which satisfy a set of equations for each one of the layer k. And for instance, in the case in which f is, say, a linear network, this equation will directly give x will be one of the data point, and this will be vt x and so this would be f of x equal xv, and this means that the weights will converge to the support vector. So the linear case you get immediately the maximum margin solution. Sorry?
You have to satisfy this for all the points, right, that are on the margin. So how can you get this with more than one point? What happens if you have more than one x star?
They will have the same value of f of x star. Right?
So you have x equal to x times.
So the equation will be the same. This equation will be the same, but f of x may be a linear, it's like the sum of different points, or the average of different points. Okay, another item to discuss later. I will not go through the Jacobian. I want to show we get so the Jacobian of f, or the Hessian, will comprise three different terms, this an, bn, and cn. Here the v are vectors, where we use a collective index for instead of the ij in the matrix. And it turns out, not going to go through it, that is negative definite for any negative, for any positive finite row, not for infinite row, not for infinite time, at which for infinite time or infinite row, the Hessian will be degenerate, but not for any finite row or any finite time. So the idea is that you get during this gradient descent on the exponential loss, what happens when you run gradient descent on a deep network, say in this particular case is the exponential loss, but I would expect the same from cross entropy. After separability, you are running into one exponential type potential hole, and there are many similar channels, so there are many minima. Each one is stable because it is in a hyperbolic minimum. They become flatter as you go to infinity. The Hessian is going to become degenerate at infinity. And so one prediction is, first of all, that after separability you are in one of these stable channels. The second one is that you'd expect to be able to jump from one of these to another minimum with a different test error, a different maximum margin solution if you perturb strongly enough. And so you're beginning to do this kind of experiment, and here is one example in which you have various epochs. This is a mini version of CIFAR, Andy. And here you have, at this point you have separability, so every data point is now classified correctly. And then there is one of the training point that is the last support vector determining the value of the function. So that's a situation without perturbations.
So that actually answers your question, Sasha. This is a case where, I mean, this is 10 class classification and there's only one support vector. That contributes the most.
Yeah, but it's possible that there could be situation with more. Sorry? I don't know whether PDF transformed correctly the next one. Maybe I have reasonably. So this is by perturbing. So here, this is separability, right? There are two support vectors, are they? So it's not yet separable, or? Yeah.
In this case, actually, just after separability, perturbation was applied, and then there were two support vectors.
Oh, I see.
And then encapsulating to a single support vector after another perturbation changes to this other minimal. There's some perturbations in the middle that do not change it, and there's another big perturbation that changes it. So the lines are, there's more perturbations out in the middle. The lines are where the perturbations cause this jump.
So this is trying to map the landscape of the minima during convergence by applying perturbation and seeing whether you jump from one solution to another. Yeah.
Sorry, what's the y-axis? Is it like a row across?
The y-axis
Index of the support vector, or index of the data points.
is basically the training points, because the function value becomes the value at one of the training points.
Is the margin for each data point? Or this is the smallest, I mean, the points are the ones that have the smallest margin. Those are the ones that go at each people.
So the perturbation is changed in the training data?
It's not changing the training data. You are perturbing the weights, not the data, and then you're running again gradient descent. If the perturbation is small, it will end up, you go back to the same. It's like you have a particle in this potential hole. You apply.
Some sort of range.
Yeah, because yes, you are. You know, for a certain fixed rho, it's like you are in a potential hole like this, something like this. You are in one of them, and then you are applying perturbation noise to the weights, and this means your point here, which is where the weights are, is the coordinates of the weight, will move because you are perturbing. But then gradient descent will bring it back if the perturbation is not big enough. If the perturbation is big enough, you will jump over, and then gradient descent will bring it down to another minimum.
This is what we see in this plot. Jumping with different sets of subordinates.
So this is a way to map the landscape where this is work in progress. I've not seen anything like this before, but I don't know whether Sasha has seen something like this, but with trying to map the landscape of the minima by perturbing the weights.
So what does that,
Sorry?
what does that mean?
Well, these are predictions you're making based on the convergence to the maximum margin and the fact that you have hyperbolic Hessian for finite rho. The prediction is that if you perturb, the perturbation is small enough, gradient descent will bring it back to the same equilibrium point. If the perturbation is large, you may jump to another hyperbolic minimum, and gradient descent will converge to that one. So that's the prediction, and that's what we find for this. So I've not seen any such attempt. Have you? There were these results by one of my students, Yuan Zhang, and Ben Recht, and a few others, about the fact that you can fit the training data with a deep network, and in other words, have zero error on the training set, and essentially being unable from performance on the training set to distinguish future performance on the test set. For instance, the most clear case was one in which they trained, they used a CIFAR set of data in which all the labels were randomized, and the network could learn to fit the data, so zero classification error on the training set. And of course, was doing very badly on the test set because it was random. On the other hand, was if you trained on the real well-labeled training set, it was also getting 0 training error, but then was going to do pretty well on the test set. So as if performance on the training set had nothing to say about performance on the test set. Okay? And this is in fact what happens with the kind of interpolating kernel networks that fit the data, even noisy data, and then may do well on future data. But these are all cases in which the training error, which is 0, does not say much about the future performance. But if you, so these are the data, these are, I think, training error and testing error, testing loss, exponential loss in CIFAR. But, the argument I just had about the results on deep networks say that what matters is certainly not a classification error on training. After some time, you have separability. What matters is the maximum margin. This will be the predictor of future performance. And so if you plot the maximum margin, you actually get a straight line here between performance on the training set and performance on the test set. And you could say from the performance on the training set that a randomly labeled situation in which you have changed randomly the labels of all CIFAR images, you can predict, you can see that the test performance is essentially, the training performance is bad. And so you will know that the test performance will have to be bad. The margin is small. So there was, let's see, a couple of additional things I want to mention quickly. One, which is kind of interesting and it's very simple, is it's an observation by that I found in a paper that I can give you the reference to, but the proof is a bit different and it's very simple, is the fact that during gradient descent you expect the weights of each layer to grow at the same rate. So if, in particular, if you start with weights at each layer that are roughly the same size, the same norm, you'd expect them to remain the same during gradient descent. It's a little bit puzzling, but the proof is so very simple. You have this equation in the W now. You let's see. You consider this derivative in time of the norm of WK, of the norm of the matrix K, and this would be chain rule. You get this expression, and this is one of the equations I derived earlier, and so the derivative of this is equal to W normalized. And so when you compute this by plugging in the W dot up there, you get, I'm sorry, you get an equation which is 1 over rho k and so on. And so if you now consider the derivative of W, the norm square, you will get this expression in which the rho k has disappeared and there is no k at all in here. So this is the rate of change in time of the norm square of WK. It does not depend on k. Let me skip this weight normalization. I said the other time that weight normalization, which is a technique similar to batch normalization that people use, is leads to the same dynamical system as the constrained normalization that we have looked at. And the key property here is to show that in the equation for weight normalization, which are this G dot and V dot, this norm here turns out to be 1. I did not see it in the papers on weight normalization, but you can prove that the norm of V is can be set to 1. So anyway, if you're interested, we can discuss that more, but let me instead discuss a little bit about what we have seen in terms of machine learning over the course, and also, personally, I'm reflecting about machine learning over the last 2-3 years or so. And even this class used to be that we are emphasizing what I would say is the classical regime. So now I'm forgetting for a moment deep networks and focusing on the classical techniques like kernel machines and similar. And so the kind of classical foundations mostly set up by Vapnik were in terms of having a finite, a fixed hypothesis, not finite, but a fixed hypothesis space. And this means having fixed, say, dimensions of the algorithms and number of parameters and so on, and then typically in terms of statement about consistency and generalization, looking at what happens asymptotically, meaning when the number of examples grows to infinity. And so because of this setup, you had concept like generalization, meaning that you have generalization when the error of the loss of the expected so the loss of the expected loss of the minimizer, or let me put it the other way, the empirical loss of the empirical minimizer, f of s, that approaches the expected loss of the empirical minimizer for n going to infinity. This would be generalization, and consistency would be that the expected loss of the empirical minimizer approaches the best you can do in the class. Now, because results like this assume that the hypothesis space, the algorithm was fixed, then these are all essentially results for number of data larger than the number of dimensions or number of parameters or so. The kind of regime that is coming out, about which, for instance, Sasha spoke last time, was in the last class, is one in which the hypothesis space is not fixed, in the sense that the dimension can increase with n. What you impose is that, for instance, the ratio of dimensionality or number of parameters and number of examples does not change while both increase to infinity. And so in this case, the notion of generalization, these are cases where, because you may always have, for all your n, you may always have more parameter than data point. You can always have interpolation, and of course you don't expect generalization to be valid or to be useful in this setup. Now, the results in the classical case were of the type that, in order to have generalization and consistency, you needed to have your hypothesis space to be a finite VC dimension, or uniform Grivenko-Cantelli for ERM algorithms. So those results stand still, and there is no contradiction with this new regime. It's just that this idea of a fixed hypothesis space or finite VC dimension don't work anymore without any contradictions. Now, an interesting question is stability. We did show, people have shown that the finite VC dimension, or UGC hypothesis space, was equivalent itself to some notion of stability of the algorithm. The idea that you have to have continuity in the inverse problem of inferring a function from the data. Stability in the sense of robustness to perturbations in the data. And that notion, although is equivalent to finite VC for supervised learning and ERM, does not seem to depend on a fixed hypothesis space, the stability itself. And so I think there is an open question of whether one can define a notion of stability that could work also for the modern regime. And just to give you some ideas, last time Sasha spoke about an analysis of the kernel solution. This would be to a supervised problem. I think you spoke about not much probably, but there is the paper more in detail about bias and variance estimate of this, and provided a complete solution. The question is whether there is some more qualitative way to connect this kind of results to notions of stability here. And an obvious one in this kind of problem, where you are looking for f of x equal to kxx. These are the kind of things we saw in the regularization classes, and this is the inverse of the kernel matrix. So the interesting question is, normally when you have something like the inverse of a kernel matrix, there is a classical notion of stability, stability of the inverse, which is usually given in terms of the condition number of the matrix. How many of you have heard the term condition number of a matrix? Have you have? Nobody? No course of linear algebra? Okay. Condition number, it turns out, was introduced in, I think, in the 40s by Alan Turing, and played a pretty relevant role in numerical analysis. It's basically how sensitive a function is to changes in the data or parameters. And it's similar to our notion of stability, in which we would like to know, for instance, in learning, how sensitive what we get as a solution is from small changes in the data. If it's very sensitive, that's not very good, because there may be noise in the data. That's true for all inverse problems. The condition number is a key concept for measuring how stable the problem is. And we spoke about ill-posed problems. Ill-posed problem, one definition is when the condition number blows up. This is an ill-posed problem. And problems with bad condition number are problems that are close to be ill-posed. So, turns out that if you look at the condition number of a random matrix, you find a double descent curve, which this is a plot of how many rows versus how many columns the matrix has. So a square matrix, when the inverse exists, has the worst condition number, and a rectangular matrix, which means either underdetermined or overdetermined, has a much better condition number. Do you find that surprising? You know, when the inverse exists, is the worst. Can be surprising. And when you have an overdetermined problem, in terms of the condition number, in terms of stability, you're much better off. Ideal condition numbers are around 1, so that any error does not blow up. If you have 120, it means some error in the data blows up in a linear problem by 120. So this would be what you have if you have if you look at problems like linear equation. It's a condition number in the case of a linear equation. How much sensitive the solution X is to noise in the data B. There are similar results, as I said, for random matrices. There are similar results for kernel matrices. This is, in fact, a kernel matrix. And so this will be like the k minus 1 in the expression for the solution to the kernel problem that I shown before. 3,500. Wow. So one question, open question, is whether it may be possible to to adapt the analysis, that such a very careful analysis, to something less careful, but that can put in direct can put direct light on the condition number of k as a key part of providing stability. I know that there is interference between the kxx and k minus 1, but